Hi everyone. So we are now going to get into rotation. So this is chapter 10 that we're starting now. Rotation will last a couple chapters and it is going to be a longer unit in AP Physics. It's a big chunk and I don't want to overwhelm you right away, but it is something that a lot of students struggle with. And I can see why. It is a very kind of abstract concept sometimes. Um, but at the same time, if you learn how to relate linear variables with angular variables right away, which is what we're going to talk about today, it is much, much easier. So remember, you know this stuff already. It's just now, instead of moving linearly, we're moving rotationally or angularly, as they say. Okay, so let's start rotation. So in this lecture, we're going to talk about relating linear and angular motion. So in this chapter, we're going to examine a rigid body rotating about a fixed axis. And what I mean by that is a rigid body is a body that can rotate with all its parts locked together without any change in shape. And then a fixed axis is just when rotation occurs about an axis that does not move. So for example, if I take my phone and I have an axis right here and we rotate it like this through that point. So the axis location is not moving and this whole body is rigid. So those points are going to rotate together. Now, in pure rotational motion, every point of the body moves through the same angle during a particular time interval. So the first variable that we want to talk about is angular position. And when I say the same angle during the same time interval, we have some reference line like this. And that same angle, same time interval was from last slide. And we can see that a point here will rotate through that same angle theta as a point here on that reference line in the same time t. So angular position is relative to a fixed direction. So we take zero angular position at whatever time we start at, or whatever position we start at time t equals 0. Usually we'll be measuring from, like, say, the positive x-axis or something like that. So they'll tell you, where you're at our time t equals 0, just like they do when we're talking about starting a stopwatch and you're at the origin or something like that. So our angular position is denoted by that theta, which of course is an angle, and that's going to be equal to s over r, where s is our arc length and r is the radius of the circle. And the circle will be, and that radius really will be dependent on which point along that reference line that we're talking about. So obviously, if we're closer to the axis of rotation, r is going to be smaller, our arc length s will be smaller, but again, that theta will be the same. And then again here, if our r is bigger, so we're farther away from the axis of rotation, our radius will be larger, but the arc length s will be larger as well. Same ratio, we still have the same angle theta. Now, it's really important to denote that and note that in this way, we have to define theta in radians. So when you're doing these problems, you want to make sure that your calculator is in radians, which is very confusing, especially when you're on the AP test and you have to convert back and forth from angle to radians in your calculator. But just remember, when we're talking about things like this, with rotation and when we're talking about arc length and radius and things like that, you have to define theta in radians. Of course, we know that 1 revolution around a circle is 360 degrees and 2 pi radians. So you can use those conversion factors in order to convert back and forth between degrees and radians and revolutions too. And here's another conversion factor. 1 radian is 57.3 degrees or 0.159 revolutions. So those are just some notable conversion factors that you might want to write down in your notes. Now, another thing that's important to note is when we come all the way around. So say that this reference line has gone all the way around and then back to its starting position, we don't reset to 0, even though our displacement of that certain point might be 0 because our starting position is technically the same as the ending position. Here, we don't reset theta to 0. We just keep recording. It's more like a distance here, a total distance of revolution. So if we have, say, 2 revolutions, that will be 4 pi radians. Now, of course, that was angular position. We also have angular displacement, just like we have linear displacement. So angular displacement is in the counterclockwise direction, is a positive direction. And the same thing here with angular position, it is important to note that the counterclockwise direction is positive. Now, the reason for this is we have a positive, like we call this a right-handed coordinate system, meaning that our positive x axis is to the right of that origin. So because of that, when we measure this angle upwards, this is our positive angle, and therefore counterclockwise is our positive direction. It's a little weird for some students to know that and remember that at first, but you'll get the hang of it. So just remember that our angular displacement in the counterclockwise direction is positive, and then if we're going clockwise, that's going to be negative. So you can see, picture here, we have a change in position of the reference line, and so therefore we have an angular displacement of that reference line, which is just equal to delta theta, or change in that angular position. Now, just like regular linear velocity, we have angular velocity. So an average angular velocity, of course, is a change in angular position over change in time, just like velocity is our change in position over change in time. Now here, this symbol right here is called omega. That's actually a lowercase omega. It's a Greek letter, and that's how we denote angular velocity. Sometimes I'll call this fancy W because sometimes people don't remember what that name of that actual symbol is. So remember, it is omega. That's our angular velocity. Okay, so this is the average, and then of course we have instantaneous, when it is changing very, 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 in a very, very, very small time interval. So if this tells us, if we know the function of that angular position as a function of time, we can just take the derivative of that function with respect to time and then find our angular velocity function from that function. Here, angular velocity can be positive or negative, and that's dependent on the sign of our change in angular position or angular displacement. Of course, if angular displacement is positive, then our omega, our angular velocity, will be positive, and if angular displacement is negative, our angular velocity will be negative. Now, the actual direction of a positive and negative is found by something called the right-hand rule, which we will talk about in a second. And then the unit for angular velocity, of course, regular velocity is a distance over time, right, or displacement over time. So we have meters per second. Here we have revolutions per second or radians per second, because we're talking about an angular displacement on the numerator of that unit. You probably have heard of the unit RPM, or revolutions per minute, which again is a angular displacement over a time. So revolutions per minute is also a suitable unit for angular velocity. Okay, last but not least, we have angular acceleration. And this is denoted by an alpha symbol. Some students will call it the Jesus fish. So this is alpha. It's a Greek letter also. And I think this is a lowercase alpha, but I could be wrong. So again, we know that acceleration is a change in velocity over time, just like we have that with linear acceleration. We have angular acceleration is a change in angular velocity over time. So again, angular velocity is that fancy W, or that omega. So we have delta omega over delta t. And then, of course, when we have an instantaneous angular acceleration, it's just when we shrink that time interval down to a very, very, very small time interval to take the change in velocity over that tiny time interval to get the instantaneous angular acceleration. So again, this also tells us that if we know the function of the angular velocity with respect to time, we can then find our angular acceleration by differentiating that function, or taking the derivative, I mean. Units for angular acceleration are radians per second squared or revolutions per second squared. Now, a big question here is whether or not angular quantities are vectors. So some of them are, one of them isn't. So both angular velocity, which is omega, and angular acceleration, which is alpha, are vectors. However, our angular displacement, which is our theta, is not a vector. And there's a reason for that, and I'll talk about that in a second. So the direction here is a little bit weird, and I mentioned this before. The direction of that omega, or angular velocity vector, points along the axis of rotation, meaning if I have something that's rotating, so here is my candle lid. So I have something that's rotating. It's rotating about an axis through the center like this, okay? Around like so. This is a very terrible demonstration. So we're rotating around the center, right? This is our axis of rotation. So what that means is that our angular velocity vector omega is going to point along this axis of rotation, which is very weird, okay? Now, the reason that it can't point in the direction of rotation is because wherever we're drawing that velocity vector, it's going to change, right? Dependent on where it's at in that object. So that's why it has to be in the same direction if we're rotating in one direction here for all of the points on this object. So that's why it's going to point along this axis of rotation. So like I said, this is really weird. It's not easy to get used to representing angular quantities as vectors. We instinctively expect that something should be moving along the direction of a vector, which is not the case. So again, as this thing rotates, we can't say that this, angular velocity vector is this way, but this angular velocity vector is this way, because they're all part of the same thing that's rotating. And of course, if it's rotating at the same angular velocity, then it all should have the same angular velocity. So it has to be along that axis of rotation, either out toward you or in toward me, right? Now, in pure rotation, the vector defines the axis of rotation. So it doesn't define a direction in which something moves. Nonetheless, the vector still defines the motion. So in order to find the direction of the angular velocity vector, we use this thing called the right-hand rule. So what happens is that we have to use our right hand, which this is my right hand. I don't know if you're watching this, if it looks like my left hand or my right hand, but of course you use your right hand. And then for the first step, you curl your fingers in the direction of the rotation, and then your thumb is going to point in the direction of the angular velocity vector. So for example, if I have this object and it's moving like this, so it's rotating this way, I would curl my fingers in the direction of rotation, right? And then my thumb points out toward you. And that's my right hand rule. So because my thumb points out toward you, that means my angular velocity vector is also out toward you. Now, if I'm speeding up in that direction, just like linear velocity, if our linear velocity is a positive and we're speeding up, that means our linear acceleration is also positive. If our linear velocity is a negative and positive and we're slowing down, the acceleration is in the opposite direction, right? So if this thing is rotating this way, and again, we know that the angular velocity is out, and say it's speeding up, angular acceleration would also be out. If it's again rotating this way, angular velocity is out, but we're slowing down, angular acceleration would be the opposite direction. All right, so that's how you find the direction of angular velocity and angular acceleration. Here's a drawing of that if my video is too tiny and it was a terrible explanation. Again, if you have this record player like this, and if you're looking at it from the top, it's moving in the clockwise direction, right? If you take your hand then and you curl it in the direction of that rotation, and I hope you're doing it with me right now, your thumb points downward. All right, so that would be the direction of the angular velocity. Again, if it's speeding up, then the acceleration would also be in the same direction. If it's slowing down, the acceleration would be in the opposite direction. Now for a magnitude, it's a little bit more arbitrary almost. You kind of just choose the length of the vector according to a convenient scale. So you could say, oh, 1 centimeter is 10 revolutions per minute. And then if it's speeding up, then 5 seconds later, it'll be larger. Very random. And then in this chapter, we really are only considering rotations about a fixed axis. So we don't really need to take these vectors into account quite yet. A simple plus, direction for counterclockwise and negative direction for clockwise will do here. Now, when we talk about angular displacement, remember we can't treat angular displacements like vectors, and the reason for this is they don't obey all the laws of vector addition. So like I said, they don't follow the rules for vector addition. So recall that in vector addition, it doesn't matter the order in which you add the vectors. Now here with angular displacement, it does matter the order in which we add the vectors. So for linear vectors, if we had like vector A plus vector B plus vector C equals some resultant vector, we could also say vector A plus vector C plus vector B equals that same resultant vector. For our angular displacement, it doesn't work like that. All right, so what happens here is say I have a book. So say I have, this is my planner that I just got for this year. So say it starts like this. I'm going to rotate it toward you, okay? And then I'm going to rotate it to my right. So that's how it ends, okay? Now, if instead I rotate it to the right first and then toward you, I'm going to rotate it to my right and then toward you. So do you see where it ended up that time? So again, first is toward you and then to my right, and that's where it ended up there. Next is to the right and then toward you. So because these things don't end up in the same location, you don't get the same result here, we can't say that angular displacement is a vector, and that's why, because it doesn't follow the rules of vector addition.